Welcome to Lecture 11. At the beginning of this chapter, we will begin to learn about operators. And so to explain some of these ideas, I will begin with some of the exercises. So let's start with exercise 4.1a. And for actually, write it a little differently. For all of the exercises labeled 4.1, or for all parts of exercise 4.1, the directions are the following. Give the matrix in the standard basis for the following operators. And so in A, the operator for which we want to find the basis, the matrix, is the following operator. And the easiest way to do this is to, first of all, make the observation that we're using the standard basis here. And let's go ahead and make sure we understand now for the first time it becomes important when we're talking about the basis that we understand not only the vectors in the basis but the order in which they are assumed to be. And what I mean by this is that for this standard basis we're talking about the kets 0 and 1 in that order. 0 is the first ket, 1 is the second ket. And the reason that's important is the following. In this 1-qubit system that we're talking about here, the first, if we want to represent these as vectors, then the first basis element is represented as 1, 0, and the second basis element is represented as 0, 1. And notice that these are column vectors. And so you can see clearly that it is important here to know the order of the vectors or the states in the basis, because the first one will appear as 1, 0, the second one will correspond to the vector 0, 1, and so we want to understand in this basis which state is first and which state is second. So this is what we mean now for the standard basis. We mean that 0 is the first state and 1 is the second state. Okay? So now that we understand that, this problem becomes fairly easy as long as we remember how to multiply matrices by each other. So let's have a brief refresher, or a brief refresher on matrix multiplication. And let's say that A is an M by N matrix. Now what that means is that if we write out A, it will have M rows and N columns. So for example, if A is equal to the matrix 1, 2, 3, 4, 5, 6, then this is a 3 by 2 matrix. because it has 3 rows and 2 columns. Now, for matrix multiplication, let's suppose A is a M by N matrix and B is a P by Q matrix. Where first of all, we can say this only makes sense when N is equal to P. So if the second dimension of the first matrix is not equal to the first dimension of the second matrix, this multiplication does not even make sense, and therefore we wouldn't write down this symbol. And the second thing we can say is that assuming N equals P, then the dimensions of AB will be M by Q. In other words, the product AB will have M rows and Q columns. Now let's look at an example. Let's keep the A that we have identified above. 1, 2, 3, 4, 5, 6. And we have already identified that this is 3 by 2. 3 rows and 2 columns, and that means M is equal to 3, N is equal to 2. So if we want to multiply A by a matrix B, the first thing we have to remember then is that the number of rows in B must be 2. Otherwise, this won't even make any sense. So we could say perhaps negative 1, 1, negative 2, and 1, 3, negative 1. This would be a possibility. This is 2 by 3. But we could also, actually maybe I should use a different example just to make sure I don't give you the wrong impression. Let's maybe do this. Add on one more column. And this is perfectly fine. We can have as many columns as B. We can have as many columns in B as we wish. The only thing that has to match is this and this. The second dimension of A must be equal to the first dimension of B. And when we multiply these vectors, these matrices together, the dimensions of, so this must be equal. And for this outer arrow, I'll say dimensions of the product matrix. So the product matrix will be a 3 by 4 matrix, and let's now go ahead and I imagine most of you have seen this before, but let's go ahead and review quickly how we would multiply A times B. Okay, so we go across the rows of the first matrix while we go down the columns of the second matrix. Now what that means is the following. First we go across this first row, 1 and 4, and down the first column. 1 times negative 1 is negative 1, and plus 4 times 1 is 4. Negative 1 and 4 is 3. Now we go across the first row and down the second column. 1 times 1 is 1, plus 4 times 3 is 12. 1 and 12 is 13. Now we go across the first row and the third column. 1 times negative 2 is negative 2, plus 4 times negative 1 is negative 4. Negative 2 and negative 4 is negative 6. And the last time now that we will use the first row of A, 1 times 4 is 4, plus 4 times 5 is 20, 4 and 20 is 24. And that concludes the first row of the product matrix AB. Now this matrix will have 2 more rows in it, and I encourage you to, if you are rusty with this procedure at all, to stop for a moment and try to calculate the entries in the second row and the third row on your own, and then come back and resume the video. Okay, so now for the second and third rows, now we start using the second row of A. 2 times negative 1 is negative 2, and 5 times 1 is 5. Negative 2 and 5 is 3. 2 times 1 is 2. 5 times 3 is 15. 2 and 15 is 17. 2 times negative 2 is negative 4. 5 times negative 1 is negative 5. Negative 4 and negative 5 is negative 9. And 2 times 4 is 8. 5 times 5 is 25. 8 and 25 is 33. And now for the last row, 3 times negative 1 is negative 3. 6 times 1 is 6. Negative 3 and 6 is 3. 3 times 1 is 3. 6 times 3 is 18. 3 and 18 is 21. 3 times negative 2 is negative 6. 6 times negative 1 is also negative 6. Negative 6 and negative 6 is negative 12. And finally, 3 times 4 is 12. 6 times 5 is 30. 12 and 30 is 42. So here is our product matrix AB, and as predicted, we predicted it down here, the dimensions are indeed 3 by 4. 3 rows and 4 columns. So that's a brief review now of how we multiply matrices, and now that we've had this brief review, we can come back up to the problem under consideration and very easily find the matrix. Okay, so we want to find the matrix for this operator here, and we have already said that the 0 cat will correspond to the 1 0 column vector, and the 1 cat will correspond to the 0 1 column vector. So that means that the operator we have here, 0 1, will be represented as 1 0. We have the column vector 1 0 corresponding to the cat 0, and now this is the bra 1. Now since the cat 1 corresponds to the column vector 0 1, the bra 1 will represent the row vector 0 1. So one more time now, we said above that the 1 cat corresponded to the column vector 0 1, but down here we have the 1 bra, so that corresponds to the row vector 0 1. Now let's make sure the dimensions are okay to even perform this multiplication. The first matrix we have here has 2 rows and 1 column, and the second matrix we have is 1 row times 2 columns. So since these ones match, this is a well-defined multiplication, And furthermore, our result should be a 2 by 2 matrix. So let's find that 2 by 2 matrix. We go across the first row. We go across the rows of this, while we go across the columns of this. So 1 times 0 is 0. 1 times 1 is 1. 0 times 0 is 0. And finally, 0 times 1 is 0. And there's our answer. Now, I won't go through every one of the exercises we're about to do and check every single one, but just for this one, for this very simple case, I think it might be worthwhile to check it and make sure that this makes sense. So let's just make a few observations. If we keep the operator written in the bra-cat form, and we let it operate on the vector A0 plus B1, well, let's see what we'll get. We would get 0, and then we now have 1 operating on this, and so we would get A. The A can come out, and we have 1, 0 plus 0 B 1, 1. And this will give us we'll have the actually we can bring this A all the way to the front, so we have A times the 0 cat, and now the inner product of 1 with 0 is 0. And then for the second term, we can bring the B in the front, and we have the 0 cat. So I can interchange the order of these two because B is just a number. And then the inner product of 1 with itself is 1. So of course this first term goes away because it's being multiplied by 0, and the second term just becomes B times the 0 cat. So in summary, when we let this operator 0, now I see why I was hesitating. We were actually asked to look at the 0, 0 operator, and instead I looked at the 0, 1 operator, but that's okay. So we'll just say practice. And so after we finish practicing with this one, then I'll break for a moment and see if you can do the 0, 0 on your own, and then we'll look at that together. Okay, so if we were looking for the 0, 1 operator, this would be what we would do. And then now we're checking it, and we have found out that this operator, 0, 1, operating on an arbitrary state, A0 plus B1, is equal to B times the 0 cat. Now let's check the matrix we obtained and see if it would give us the same conclusion. Okay, so we have, we're going to replace the operator. If this matrix really is the correct matrix, then we ought to be able to replace the operator with it. And now we have to replace this. We have to put it in vector form too. Now, how would we do that? Well, A is just a number, so we bring down the A. But the 0 ket, remember, that corresponds to the 1, 0 column vector. And we bring down B, and the 1 ket corresponds to the 0, 1 column vector. And so I'll put equals with a question mark because we don't know if this is going to work out or not. Now for the right hand side, we bring down the B. And for the 0 ket, okay, again we have the 1, 0 vector, column vector. So now let's see if this all works out. Well, let's simplify on the left hand side this term in the parentheses first. We will have A times the column vector 1, 0 is the same as the column vector A, 0. And B times the column vector 0, 1 is the same thing as the column vector 0, B. And over here on the right hand side, B times the column vector 1, 0 is B, 0. Now it's not perfectly clear yet if this is correct or not, so let's go one more step. In fact, a couple of more steps. So we have 0, 1, 0, 0. And now when we add the column vector A0 to the column vector 0B, we get the column vector AB. And we ask if that is equal indeed to B0. And now we're ready to do our matrix multiplication. So we go across this row and down this column, and we'll get 0 times A is 0, 1 times B is B, 0 and B is B. Now go across the second row. 0 times A is 0, 0 times B is 0, 0 plus 0 is 0. And sure enough, we see that we do indeed obtain B0. So it looks like this method has worked out, and we have found the matrix. It looks like indeed the matrix representation of this operator 0, 1 is in fact the matrix 0, 1, 0, 0 if we're using the standard basis. So now I very strongly urge you, so now find the matrix for 0, 0. So stop the video, give this a try, and then resume the video and make sure that you got the correct answer. Okay, so I hope that that was pretty straightforward for you, but let's now all do it together. We know that the first 0 can be written as 1, 0, the second 0 is 1, 0 here, and now if we multiply this out, we get 1, 0, 0, 0. And that should be the matrix that you obtained for this problem. I guess I shouldn't put a check mark, but I didn't check anything there, but this is indeed the answer you should get for part A of exercise 4.1. Now let's look at another one. Let's perhaps look at C. This one is interesting because it's dealing with 2-qubit states. Okay, so for C, the operator that we want to consider is the following. Okay, now Once again, just as was the case in problem A, so it is the case in problem C as well, that we need to have a very clear understanding of what the basis is in this case and the ordering of the basis. And it's different now from what it was before, because in problem A, we were talking about a 1-qubit system, but now we have a 2-qubit system. So what is when we say we have the standard basis, but it's a 2-qubit system, what do we mean? So standard basis for a 2-qubit system well, I think you probably know what this is. The first one is 0, 0. The next one is 0, 1. The next one is 1, 0. And the fourth and final one will be 1, 1. So, and this is the correct order: 0, 0, 0, 1, 1, 0, 1, 1. So when we want to find the column vector corresponding to these, now we're in 4 dimensions, because we have to have 4 basis vectors here. And we will list the first one as 1, 0, 0, 0. The second one will be 0, 1, 0, 0. The third one will be 0, 0, 1, 0. And the fourth one will be 0, 0, 0, 1. Okay. Now, now that you have that information, I believe that you should be able to finish this problem very easily. So I encourage you to stop the recording, give it a shot, and then let's all look at it together. Okay, so for this problem, the work is once again very simple. Okay. So 0, 0, remember, is the 0, 0 ket is represented by 1, 0, 0, 0, that column vector, and the oops, I have an error here. Oh no, sorry, this is correct. So we have 1, 0, 0, 0, and then when we take the bra form of that column vector will become a row vector. So we'll have this plus 0, 1 is the second one. So we have 0, 1, 0, 0, and then 0, 1, 0, 0. And let's multiply this out and see what we get. And notice that this is a 4 by 1 matrix. This is 1 by 4. This is 4 by 1, 1 by 4. So the dimensions all work out to be correct, and we expect to get 2 4 by 4 matrices, which we will then add together, since this is addition sign, to get a finally 1 4 by 4 matrix. So let's see how this goes. Well, the first one will be 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. And the second one will give us 0, 0, 0, 0, 0 1 0 0 0 0 0 0 0 0 0, and then when we add these two matrices together, we get the following. And there is our answer. So that's the way that we would do a problem for a two-qubit, an operator on a two-qubit system. So let's perhaps do one more, and then we'll move to something else. We want to find this operator, and they even are reminding us of the identity of psi plus So, strongly encourage you to stop the video now, try this for yourselves, and then we will then come back and check your work. Okay, the reason that I wanted to have a little break there was that this seemed wrong to me, and in fact it is wrong. This is what is written in the textbook, but if you refer back to an earlier page, let's see here if you refer, for instance, to page 39, you will see that this vector here, this state is not psi plus, this is actually phi plus. And so since we're being asked to find this operator, we want to make sure we use the correct expression here. And so again, if you look at page 39 in your text, you will see that the correct value here, we should have 0 1 plus 1 0. This is the correct expression for psi plus. Okay, so now that we have the correct expression for psi plus, we can go ahead and finish this problem. Oh, and by the way, I guess perhaps some of you went ahead and did it the other way. So let's see here if I can. Well, I guess. Okay. What we'll do is I'll go ahead and show you what this correct answer is, but then I'll show you what the answer would have been for the problem if you went ahead and did all that work. If you did not catch the little error that we were actually had the wrong, the book had the wrong identification for C+. If you didn't catch that and worked with the original numbers, I'll show you how to do that as well. Okay, so let's suppose first that we'll do this assuming that you did catch the error. So we have 0 1 plus 1 0, and so therefore this remember 0 1 corresponds to the vector 0 1 0 0, and 1 0 corresponds to the vector 0 0 1 0. So the vector corresponding to psi plus is actually, when we add these together and then multiply by 1 over square root of 2, we will get 0, 1 over square root of 2, 1 over square root of 2, 0. That is the column vector that corresponds to C+. And for those of you who worked with the original vector that was given, the 0, 0 plus 1, 1, that is actually phi plus. So let's go ahead and see what you would have gotten. Well, 0, 0, that corresponds to the column vector 1, 0, 0, 0, and 1, 1 corresponds to the column vector 0, 0, 0, 1. So you would have obtained 1 over square root of 2, 0, 0, 1 over square root of 2. If you use the correct, the original value that the book had for C+, this is the column vector right here. This is the column vector that you should have had. And now we are ready to do this problem. So the column vector C plus becomes 0, 1 over square root of 2, 1 over square root of 2, 0, and then that will get multiplied by the bra form of that same. So 0, 1 over square root of 2, 1 over square root of 2, 0. And so let's see what happens. We will get for the first row 0, 0, 0, 0. And for the second row we will get 0, 1 half, 1 half, 0. And then for the third row 0, 1 half, 1 half, 0. And finally for the last row 0, 0, 0, 0. So this is the correct answer to this problem. But if you worked with the values that were originally given, then let's see what we would get. Okay? So in other words, if we did phi plus, what would we get? Well, in that case, we would get 1 over square root of 2, 0, 0, 1 over square root of 2, 1 over square root of 2, 0, 0, 1 over square root of 2. And when you multiply this out, you would get 1 half, 0, 0, 1 half, 0, 0, 0, 0, 0, 0, 0, 0, 1 half, 0, 0, 1 half. So if you worked with the original numbers, that's the matrix that you should obtain. So I hope that now, after going through several examples of exercise 4.1, it is easy to go from the bracket form of an operator to the matrix form. And now in exercise 4.2, we're going to be doing exactly the opposite. We have, so in exercise 4.2, the directions are write the following operators in bracket. Notation. So let's do a couple of these as well, and then we'll look at some problems for this section. So let's start off with A. It is the Hadamard operator, which is worth knowing. Hadamard operator. And it is usually denoted H. And in the case of a one-qubit system, the Hadamard operator will have this form: 1 over square root of 2, 1 over square root of 2, 1 over square root of 2, minus 1 over square root of 2. And now we need to ask ourselves, how do we express this in bracket notation? So I'll give you a moment to think about this, and then we'll all look at it together. Well, I believe that perhaps the easiest way to do a problem like this is to go ahead and begin by making a few observations. If we're working with a 1-qubit system and we have the standard basis, for 1-qubit system, we have this, and we remember that the associated column vectors will be 1, 0, and 0, 1. Now, if we think about this for a moment, the operators that are possible in this case are, you might think of it as having a basis for the operators, and that basis will contain 4 basic operators, and any operator can be written as a linear superposition or linear combination of those 4 operators. What I mean is this: we would have 0, 0, 0 is one possibility, 0, 1 is another one, 1, 0 is still another, and finally 1, 1. Those are the 4 operators that we could, or those are 4 operators that form a basis for the set of all the operators that we could have operating on this 1-qubit system. And if we look at the matrix form for each one of these, well, here we would get 1, 0, 1, 0, which would give us 1, 0, 0, 0. Here we would have 1, 0, 0, 1, which would give us 0, 1, 0, 0. For the next one, we would have 0, 1, 1, 0, which would give us 0, 0, 1, 0. And then finally, for the last one, 0, 1, 0, 1, and 0, 0, 0, 1. Now, the point of doing this is to make the following observation. If we look at any arbitrary matrix, A, B, C, D, well, that can be written as A times 1, 0, 0, 0 plus B times 0, 1, 0, 0 plus C times 0, 0, 1, 0 plus D times 0, 0, 0, 1, which corresponds to, so we can say A, B, C, D, that matrix corresponds to A times the 0, 0 operator plus B times the 0, 1 operator plus C times the 1, 0 operator plus D times the 1, 1 operator. And now that we see that, any 2 by 2 matrix, it becomes a trivial matter for us to write down the operator in bracket notation corresponding to any 2 by 2 matrix. So for instance now, if we return to the problem under consideration, the Hadamard operator, H equals 1 over square root of 2, 1 over square root of 2, 1 over square root of 2, minus 1 over square root of 2. What is the corresponding operator? Well, it will be 1 over square root of 2, 0, 0, plus 1 over square root of 2, 0, 1, plus 1 over square root of 2, 1, 0, minus 1 over square root of 2, 1, 1. So it becomes just that simple to do any 2 by 2 matrix, to find the operator corresponding to any 2 by 2 matrix. So I believe that parts B, C, and D of this exercise would be trivial for you. So now let's think about perhaps part E. I don't want to work out part E in detail. I just want to comment that here we have a 4 by 4 matrix which corresponds to operators on a 2-qubit system. So now I'll just say that what you should do is to consider the basis 0, 0, 0, 1, 1, 0, 1, 1. And if you look at this with itself, you'll get one operator, this with this. What I'm saying is you're going to get 16 different operators altogether, and just to begin listing a few. So we'll have this, that's the first 4, and then you would keep on going, and finally down here will we get 1, 1, 1, 0, 1, 1, 1, 1. So if we found the matrix corresponding to each one of these operators, we would find that each of those matrices, each of those 16 matrices, would be a 4 by 4 matrix that would be 0 in all of its entries except for 1, and it would have a 1 in that one entry. Just like here, when we did the 1-qubit system, we got 4 2 by 2 matrices, and each one of those was 0 in all of its entries except for one entry, and in that one entry it had a 1. Well, likewise now when we go to the 2-qubit system, we will get 16 4 by 4 matrices, and each one of those will have 15 zeros and just one 1, and so you can find the matrix for each one of these and then find a general formula for the 4x4 matrix, just like here we found the general formula for the 2x2 matrix. So that would be tedious, but it's a straightforward problem. So that's how you would do E. And now the last thing I want to discuss before assigning problems is how to do a problem of type F. And so they want us to look at X, the tensor product of X with X. Now, you need to look above, and you need to look at earlier in the problem to understand what X is. X is 0, 1, 1, 0. So this is an operator on a 1-qubit system. This is going to be an operator on a 2-qubit system, and we want to find the we want to find that operator in Brock-Cat notation. So I'll give you a moment to think about that, and then we'll all look at this together. Okay, for this problem, I want to consider two different ways to do it. In the first, we will go directly to the Brock-Cat notation. So we learned in our work here on part A of this problem that X corresponds, when we put this operator in Brock-Cat notation, it corresponds to 0, 1. That is the we see that from the 1 in this position, plus 1, 0, and we see that from this one. And so now, if we want to take the tensor product of X with itself, we will have the following: 0, 1, plus 1, 0, and then tensor product with the same thing: 0, 1, plus 1, 0. And let's see what we would get. Okay, the first term will be 0, 1, tensor product 0, 1. The second term will be 0, 1, tensor product 1, 0. The third term will be the tensor product 1, 0 with 0, 1. And the final term will be the tensor product 1, 0 with 1, 0. Now the way that we evaluate each of these tensor products is the following. We will get, for this first tensor product, we get 0, 0, 1, 1. For the next one, we will get 0, 1. This is the first bit, the 0 and 1, the first bit of each operator expression. And then we're going to take the second parts of each operator expression. So 1, 0. For the next one, 1, 0, 0, 1. And then finally 1, 1, 0, 0. So once again, we look at, and each one of these operators consists of a cat and then a bra. Cat and bra. Cat, bra, cat, bra, and so on. So when we take the tensor product of two of these operators with each other, we look at the cat parts together, 0 and 0, to form this, and then we look at the bra parts together, 1 and 1, to form this. Again, the cat parts, 0 and 1, the bra parts, 1 and 0, and so on. Now that we have the operator written in this form, now we simply need to remember the column vectors corresponding to, the column vectors corresponding to each cat in the basis, and the row vectors corresponding to each bra. And so we get 1, 0, 0, 0 here, and then 0, 0, 0, 1 for that, 0, 1, 0, 0 here, and 0, 0, 1, 0 there. Zero, zero, 1, 0 there, and 0, 1, 0, 0 here, and finally 0, 0, 0, 1 and 1, 0, 0, 0. And this is the column vector corresponding to this, and this is the row vector corresponding to this. And we've just used all of the information that we've already covered in this lecture to fill in the rest of those. Now let's compute each one of these. We will get, for the first one, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. For the second, we will get 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0. For the third one, we'll get that. And finally, for the last one, we will get this. And now when we add all of these matrices together, we get 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0. So this is the answer right here. This is the answer in matrix form that we would obtain for the tensor product of x with itself. But actually, remember, we're asked for the bracket notation, and so we found that up here. We could have stopped at that point. But it's useful to have the matrix notation, because that leads into the second way that I wanted to show you to do this problem. So once again, the first way is to go ahead and take each one of these operators, express it in the bracket notation, and then take the tensor product of the two terms that you have. And remember that when you take these tensor products of terms, you have ket, bra, ket, bra. Remember that when you take the tensor product, you'll group the kets together in the first term and then the bras together in the second term. And that's true for each one of these. And so you got this answer, and this answer is your final answer. But if you wanted to find the matrix form, it would be given here. Now I'd like to show you another way, a quicker way to find the matrix form. And I'll do this in a general sort of way. Suppose, let's say R is equal to A, B, C, D. Then the tensor product, well, actually, let me go ahead, make this even more general. And let's suppose S is equal to E, F, G, H. Then the tensor product of R with S is actually the following. It is A, you take the first element of R, so you have A times the matrix E, F, G, H. And likewise here you'll have B times the matrix E, F, G, H. C times the matrix E, F, G, H. And then D times the matrix E, F, G, H. And so you end up with the matrix AE, AF, BE, BF, AG, AH, BG, BH, CE, CF, DE, DF, CG, CH, DG, DH. I'm laughing now because I just realized that probably, I think there was a fair amount of dog barking. I'm so accustomed to it, I don't even know. But I think there was a fair amount of dog barking during my explanation, so I hope that was not too distracting. But anyway, this would be the way to do that, get directly the matrix form of the tensor product. And just to check it with X, tensor product X, and this is a check because we've already calculated it up here. But let's just see that with this new method we'd come up with the same answer. Okay, X, here is our matrix for X. So this would be 0, 1, 1, 0, tensor product 0, 1, 1, 0. And according to what we just said, this would be 0 times 0, 1, 1, 0. 1 times 0, 1, 1, 0. 1 times 0, 1, 1, 0. 0 times 0, 1, 1, 0. And let's see if this does indeed turn out to be right. So we would get 0, 0, 0, 0 here. 0, 1, 1, 0 there. 0, 1, 1, 0 there. And 0, 0, 0, 0 here. And sure enough, if you compare this answer here with the one up here, you see that we obtained exactly the same answer. So that's a quicker way to get the tensor product of two operators when they're given in matrix form. So this gets us a good start on chapter 4, and now let's look at some problems. So now to finish up this lecture with a few problems that I think you'll find fairly straightforward. In problem 11.1, you are asked to give the matrix in standard basis for this operator. We have the ket 0, 1 and the bra 1, 1. And you can see the 4 matrices given here. And in each case, all the entries are 0 except for 1, and that one non-zero entry is equal to 1. So here's the non-zero entry in A, here's the non-zero entry in B, here's the non-zero entry in C, and the non-zero entry in D. Which one of these is the correct matrix for this operator? And in 11.2, you're given a matrix operator and you're asked to find it in bracket notation, and we have these 4 choices given here. So you find which one is correct, and then in class we'll have one more problem. So good luck with those problems, and that concludes lecture 11.